Hello everyone. In today's class, we are going to discuss about the computer organization and design. So in this chapter, we are going to discuss about the basics of how your computer is designed, what are the different registers which we have, how the buses interact with each other. So we are going to discuss about all those topics. We are also going to discuss what is a common bus system, how the computer actually performs the computations, how the registers are connected with each other. So that is what we are going to cover in this chapter. So every processor which we are going to use has its own design. So there are different registers, they have different buses, they have different micro operations, their instructions are also different. The modern processors which we are using, it might be i3, it might be i5, it might be i7. So every processor which we are using right now is very complex. So the what we are going to do is in the class to make these things simplified so that you are able to understand it properly, we are going to use a processor which is quite old, because even if the basic thing will remain same, even if you are constructing a bigger architecture of that processor, still the basics will remain same. And secondly, whenever we talk about companies, they don't publish their inventions. Like if there is a i7 which is in the market, so they are not going to launch any kind of public paper about the architecture of that particular processor. So in this class, we are going to discuss about a processor which is quite old, but still you will be able to understand the basic concept that how a processor interacts and how the different parts of that processor work with each other to achieve a task. So this is the basic computer which we are going to consider. So in this computer, we are having one RAM which is having the storage from 0 to 4095 bit. 4095, which comes out to be 4096 total number of bits. Now in this memory, what we are having, one word which the memory has is of 16 bit. You can identify it like it is mentioned that you are having each word which is a 16-bit long. So if it is 4096 into 16, so we can simply identify how many number of what is the size of that memory. So it is simply, you can do it with the help of a calculator as well. So it will be 4096 into 16. So it is 65536. So these are the total number of bits inside the uh, your memory. So 65536. So these are the total number of bits inside your memory. That is how we calculate it. So in this, what this 16 bit says, according to this circuit, this 16 bit just signifies that there are 16 bits in one word, and there are such 4096 into 16 number of total bits inside the memory, and there are 4095, because we are going to start from 0, so there are up the last address which we are having is 4095. These are the total number of words which we have, that is 4096, and each word is having 16 bits. After this, how many bits do we need to assess these 4096 total addresses? It will be 2 raised to the power 12. Now how? Because 2 raised to the power 12 is 4096. Because 2 raised to the power 10 is 1024, 2 raised to the power 11 is 2048, and then it is 4096. So how many total number of address lines do we need? Are only 12. So by using 12 bits, we will be able to access all these 4096 locations. So we can do that by using the 4096 locations. Now let us move to the next part. So this was about memory. Now simply, if it is 1024 and 216, it simply says there are 1024 words, and in each word there are 16 bits. This is just an example. Now let us move to the next thing, that is an instruction. Now what is an instruction? In instructions, what we have a sequence of instructions which combine to make a program. So first of all, let us talk about a program, then we will talk about the instructions as well. Now, program is just a sequence of instructions. Now, what is a machine instruction? Like we talked earlier as well, if I'm writing add R1, R2, so this is one instruction. If I write such 5 or 10 statements, then it will become a program. Now, all the instructions which we have, they are going to be stored inside the storage inside the memory. So everything will be stored inside the memory along with the data which we require. So in such a case, like add R1, R2. So these are the two registers. So it means the data should be stored on these registers. But it is not always that there can be a register only. So we can have certain address in the memory. So we can use these two addresses, operand and all that address. So we are going to store the address as well. So it is not only that you can only have registers to perform the operation, you might have addresses of the memory as well. Now, then how the system or how the CPU is going to process the data. There is one register known as IR, that is an instruction register. From its name, it's clear that it is going to store the instructions. It is only going to store the instructions. Whenever your CPU reads the instruction, it places it inside the instruction register. It stores it in the instruction register. Now, there is a sequence of operations which happen to identify that what type of instruction is it. Like we can have a add instruction, we can have a divide instruction, we can have load instruction. So all the instructions are different in their nature. So we need to identify that the what type of instruction is this which is stored inside the instruction register. So we need to use a circuit to identify the type of that instruction. Now the next thing which we have, now this is an instruction which is getting stored in a register IR. This is a IR register. So there will be certain format of that instruction which we are going to store. It is not possible that in one case we are going to store the address at the end and operand at the start. And in some case we are going to store the operand at the end and addresses in the start. It is not like this. So we need to have a specific format to store an instruction. Now format, you understand that how you are going to write the instruction. So it is that instruction format which your system always follow. So your system is having a particular format in which all the instructions will be written. So that is why whenever you are talking about any type of high level language like C, C++ and all those your Java or any language, so there is a specific format and in which you can write the code. So that code is due to the instructions which we are having. They need to follow a particular format those instructions, when once they get converted into the low level instructions, so they need to have a particular format. So that is why we need to follow the format. So every instruction has a format in it. So let us talk about the different parts of that instruction. Now, see, if I take the same example which we did earlier, this is add, then let's talk about the value C and D. Just write it like this. Add is a opcode. Okay, it is also known as operation code. This is a opcode, and these two are the addresses where we are going to perform the operation. So this will be known as opcode. The later parts are known as addresses. Now, in every instruction, we need to have a opcode and address. But when we will move forward, you will able to see that in some of the instructions there are different instructions. So in some of the instructions, this address will be given inside the opcode directly. So we will also talk about that as well. So now, beforehand, let us move to the basic format. So inside this, I have only explained that there is a add operation. If this is an example, add is an operation, so it will be known as opcode, and these two are known as addresses. Now let us talk about the same computer which we discussed earlier. So in the inside that instruction, we were having a basic computer which was containing a memory of 4096 into 16 bit. So it was something 4096 into 16 bits. So that was the total size. Means one word was containing 16 bits in it. So that was what we were having in the basic computer. And to access these 4096 bits, we need 2 raised to the power 12. We need 12 bits to access all these 4096 words. Now, let us talk about the addressing format which we have, or instruction format which we are going to obey when we want to perform any operation inside the system. So how we can do that? So there are different things in it, there are different parts of the instruction format. So this is an important part, please remember this. Instruction format. So inside the instruction format, the total length which we decided will be remaining same, because the maximum size which our memory can store is of 16 words, 16 bits, because it was 4096 into 16. So maximum length which we have chosen is 16 in this case. So if this starts from 0 and ends at 15, so there are 16 bits. So there are 11 bits, up to 0 to 11 means total 12 bits. They are reserved for address. This will be the address from 0 to 11 means 12 bits. Then starting from 12th bit up to 14th bit, there will be a opcode. And the last one which we have, that is the addressing mode. ADD addressing mode. So this thing is very important. You need to know, you should be aware about it. What is an instruction format? Then what are the different parts of that instruction format? So this is very important. So from 0 to 12, 0 to 11, there will be the address. From 12 to 14, we are going to have opcode. and then in 15th bit we are going to have the addressing mode. Now what are these values? What is our address? What is our opcode? What is our addressing mode? So we are going to cover it in the next slide. Now we are having a example at this place, so we will just talk about that. So let us firstly address this part. What is a addressing mode? So there are two type of addressing modes. One is direct, second is indirect. So if the value at this place is 0, it is a direct address. If the value is 1 at this place, then it is a indirect address. Indirect address. Then after this we have a opcode. Now let us take an example which is given in your slide. So what they have mentioned it is 0, add 457. If I want to put it inside the instruction format, so what it tells, this part is a address, this part is opcode, and this part is addressing mode. So if I want to identify whether it is a direct address, whether it is an indirect address, I need to pay attention to this place, whether it is a 0 or 1. If it is 0, it is a direct address. If it is 1, then it is a indirect address. Direct address and indirect address will be identified by using this value which we have on the most significant bit. This value will tell what is a uh, type of address, direct or indirect. Now let us differentiate the direct address from indirect address. So we are going to take the same example which you have in your slide. So how we can differentiate? So it is, what is the difference between a direct address and an indirect address, which we are going to cover in this uh, slide. So let us just make the same diagram which we are having. I will just let you know how it is going to make a difference. Now this is a add operation. This is 457. This is 0. This address is 22. Just assume this is the 22 address. Then after this, this is the complete program, and inside the complete program we are having another address which is 457. Now, as we discussed earlier, in the instruction format we have three different parts. So first part is the addressing mode, which is this one. Then second is the opcode, and third one is the address. Now what is the this address? Like if I write add 257 and this is 0, so it simply says that the operand is at this place. You can get it from this address. So in this case, when it is a direct address, it simply tells you that the operand is at 200 and 457 address. So once this is there, you get the operand, you perform the add operation, and then you store the data. So AC is accumulator. Accumulator is going to be a general, you can say, process register, which is going to store the results after the calculation. So it is going to store the data. So what it tells, it is telling that this is the 22 22nd address where the instruction is of add, and the address which is mentioned is direct address. Means this address which is mentioned is the address of the operand directly. So the operand is stored at this place whatsoever is the operand. Like if I want to perform add 51, This is just what I want to perform. So this is 0. So what it tells, it is telling that the actual operand which I am having is at the address 51. So I will get it on the address 51 whatsoever is the operand. So at this place 51 I will be having a operand stored. Now what is a operand? Like if I want to perform the addition, so for performing addition, I will have one value with me or two values with me. So if I want to perform addition, I will have a value A, I will have a value B. So these two values are known as the operands. Like in the case of if I want to add 20 with 30. So 20 and 30 both are my operands. So in this case, this add 457 is telling that these two values which I want to add are stored at 457 location. So this is a direct address. This is a direct addressing. It is a direct address. Now let us contrast it with a indirect address. Now in the case of an indirect address, the value which we are going to talk about is not directly stored at this location. Now in indirect address, rest everything will remain same. This value is going to change to 1. Add, it might be 457 at this place. There is no such thing that it can't be there. So if I do it with the same example, this is 457. But if it is an indirect address, it simply signifies that my operand is not stored at this place. My operand is at a different location. So from where I will get that actual address of the operand? From this location. So I will visit at 457. So at this place there is another address mentioned, like it might be 1000 or it might be anything. So the address which is mentioned at this place, I will need to visit at that place or at that address, and there I will get my operand. And once I get the operand, then we are going to perform the add operation, and our result will be. Are you able to? I hope you are able to understand it. So both I have taken the same example instead of taking the different example. I have taken the same example in this case so that it will help you to understand. If it is a direct address, you can identify it from this value whether it is 0 or 1. If it is a direct address, then this 457 will tell that there is a operand stored at the location 457. Go and get it from here. Then if it is an indirect address, this value will be 0, and this address which is given, it is not telling the actual address. It is only telling that from this address you can get the actual location of the address. So it is 1000. So I will be able to get the value of 1000. What is the operand at the location 1000? So I need to visit at 1000 again, and from there I will get the operand. Now there is a basic question which you have, which you should have or you will have in your mind, that is if direct address is better, because in direct address I'm having the direct value, it will take less time to calculate because I'm directly getting the address. But in the indirect I will need to visit firstly to this place, then to this place, so it will take more time. Yes, it is correct. The indirect addressing takes more time. It is absolutely correct. The thing is, why do we need the indirect address? Because sometimes it is not possible to directly give the address. Like in the case of your pointers, we have we point to a particular location. So when we are using the pointers, we are not directly giving the address, we are using the indirect addressing in that case. So that is why it is important to have direct and indirect addressing available. Now There is one another concept in this, that is EA. EA is effective address. Effective address. So you need to calculate this effective address when we are going to perform any type of operation. Now let us see what is a effective address in the first case. So this is a direct address. So 457 is the address which is given. Now let me firstly tell you what is the effective address. Effective address is that location where you are directly able to find your operand. So simply where you find the operand, that is your effective address. So in first case, what is our effective address? That is 457, because at 457 we have got our operand. So in the first case, the effective address will be 457. But in the case of second value, second case, it is a indirect addressing. So in indirect addressing, the indirect address which is mentioned to me, that is 457, but my operands are not there. So where my operands are stored, that will be the effective address. Now in this case it is 1000. So effective address in this case will be 1000. So this is what effective address means. So the address which we are going to use to access the operand will be my effective address. In this case, it is 457, but in this case, it is 1000. So that is our effective address. So the concept which we are going through right now is direct and indirect address only. So we are having different type of addresses which will be there. Around 15 type of addresses are there. So we will discuss that in the next chapters. We are not going to do it before midterm, I think. So next is processor registers. What are the different processor registers which we have? Like we have discussed about AC, we have discussed about EA, we have discussed about AR, IR, we have discussed about DR. So we are just going to briefly get the introduction about what are the different registers and what are their different operations which they perform. So first of all, the very basic, or you can say most important, which we are having, which you need to remember, is PC. It is known as program counter. Now, what does this PC store? It always store the address of the next instruction. Please remember it. It stores the address of next instruction. It stores the address of next instruction. This is very important. It doesn't store the address of current instruction. It stores the address of next instruction where I need to move. So that is what it stores. So this is the task of program counter. Then the next register is AC. Sorry, we can talk about AC, we can talk about AR, it is up to you. So it is a accumulator. Accumulator. Now this accumulator is a general purpose register. It is a general purpose register. Now what does it store? Whenever we are calculating two values, there might be some intermediary results. If we are calculating an instruction, there might be some values which we get as an intermediary result. So Accumulator is going to store that. It is going to store the temporary values. It is going to store the results. If there is no destination given, it will automatically get stored in a accumulator. So like if I am having an example of like add R1 R2. So this is going to perform what? Add the content of R1 and R2 and store the result in R1. This instruction is as well as valid. Add R1. Now where it has to add? It will add it with the value of accumulator and store the result in accumulator. So this add R1 directly, it simply says that just add the content of R1 with the content of accumulator and store the address in accumulator. So accumulator is simply a general purpose register which can be used for various tasks, and it is the register which is connected with your ALU. So most of the times ALU will be accessing your accumulator only. So whenever you are going to perform any type of calculations or anything, accumulator will be used. So accumulator is a general purpose register. After this we are having AR. It is the address register. Now this address register is going to store the address inside your computer. So if you remember, in the basic computer we said that there are 4096 total locations starting from 0. So we were having 4095 locations total. They are 4096. And how many address lines do we require? So the total number of address lines which we were requiring was 2 raised to the power 12, because that is equal to 4096. So how many bits in the address we require? 12. So the total address register bit length is 12 bit. The reason is this: the memory which we are using. The memory is 4095, so address register is of 12 bit. So in this case, when we are talking about the examples or whatsoever calculations we are taking, we are only talking about the basic computer, which assumption we have taken already. So it is according to that assumption. So 2 raised to the power 12. So it means the address register is going to have the length of 12 bit. Then after this, there is a data register. Now DR is its name. So we can name it as DR, which is a data register. Now in the case of data, this was the memory. So total 024095, and how many address bits we were requiring? 12. And how many number of bits were stored inside one word? They were 16. So how much data was stored? 16 bits. So at one time, if my data register want to store a value, it should have the length of 16 bit. Only then it will be able to store this one word inside it. Its name is data. So data is available at this place. Data might be a instruction, data might, everything is a data. Whether it is an instruction, whether it is a operand, whether it is a opcode, whatsoever is there, it is a data. So data length of the register length of for the data should be 16 bit, because it is going to store these 16 bits which my memory is having in one word. So this one word value, which is a 16 bit, will be stored here. Now if one word is containing 32 bits, so then definitely we will require a data register of 32 bit. Now the thing is, in our case which we have considered, we are considering that there is a 4096 total words, and one word is having 16 bit of one word contains 16 bit. So that is why this data register is of 16 bit. If you increase this value, your data register, your address, and if you increase this value, then your address register bits will also increase. According to that, everything is going to change. So similarly, If we talk about this program counter, it is going to store the address of next instruction. It is going to store the next instruction. How many total number of instructions can be there? It can never be more than 4096. So definitely what will be the size of this program counter? 12, because the total number of instructions can be only 4095 4096. So then it should be 12 bit. So that is how we decide that what will be the length of our different registers. So it basically depends upon the assumption which we have taken for a general purpose computer, that there is a 4096 bits of 4096 addresses, and there are 16 words inside a memory. So according to this, are all the registers are going to possess a size. Now let us move to the next registers. So after DR, we have another register known as TR. It is a temporary register. Now it will store the intermediary result, like we are having some temporary results, so those will be stored in this. Like we were having our general purpose register as well for this task. So these both are going to perform the you can say temporary register will store the only intermediary results, whereas accumulator is going to store those results which it has calculated after performing the operation. But this will store the temporary data only. So if it is going to store the data, so you can assume what will be the length of it, because data is of 16 bits, so TR is of going to be of 16 bits. Then we have two more registers. One is INPR, one is OUTR. This is a input register. What are the inputs which we are going to get from the outside? So if you press a key on your keyboard, it gets collected in INPR. So INPR collects 8 bit of data, means 1 byte of data at once. INPR is of 8 bit, OUTR is of 8 bit. Input register is going to get the input from the user. Whatsoever type of input we want to give, it will always go through INPR. In INPR, you might include the keyboard, mouse, mic, whatsoever you are connecting, that will be moving to input register. And OUTR holds 8 bits of data or 1 byte of data, and it will be showing you the output from your processor. So that is the OUTR, output register. Now there are basically the registers which we have discussed are PC, AC, AR, DR, TR, INPR, and OUTR. So you need to remember them. Then we have that is memory. We have MAR, so we will discuss about that. Now why I am saying you to remember this, at least you need to know what is their functionality. Now why it is required? We are having a next type of bus which we are going to create, and the name of that bus is common bus system. This common bus system needs to use all these registers, because common bus system is something which we use to uh, transfer the data from one place to another inside the processors. So processor is going to have these registers, and the bus system which is used by these registers is known as common bus system. Now how it is different from a 4-bit bus system or a 8-bit bus system? What is the difference? In common bus system, we are having different sizes for different registers. But in the case of 4-bit registers or 4-bit bus systems, we were having all the registers with 4 bits. or we were having all the registers with 8 bits. But now in this common bus system, we are having different registers and there are different sizes of those registers and they are connected with each other. So we are going to use it inside the common bus system. But don't worry, the concept will be remaining the concept will be similar of this common bus system and your 4-bit bus system. There is a small 4-bit bus system inside the circuit. So we will discuss about that. So in the next slide, we are just having the explanation of what is the size of the different memories which we are using, what is the task, how much, what will be the address. Okay, so I think we have missed out the instruction register in it. IR, that is an instruction register, which is going to store the instructions, and the size of the instruction register will be again a 16-bit data. It will be of 16-bit because whatsoever we are going to store inside the memory will be known as an instruction, whether it is a instruction or data, but it will be processed as a instruction. So at complete, we are having 8 different registers: PC, AC, AR, DR, TR, INPR, OUTR, IR. So in the next slide, we are going to construct the common bus system. So we will discuss about that in the next lecture because I think we are not having that much left now. So we will discuss this in the next class. So we how we are going to construct the common bus system, why the memory unit is near to AR, why PC is there, why DR is there. So we will discuss all this in the next class. Thank you everyone. Thank you so much.